Hi students, welcome to my lectures on chemical engineering thermodynamics. I request you to follow from the lecture 1 to understand what is happening because everything is connected. In the today's lecture, I am going to introduce an important property which is useful in application of thermodynamics, which is called partial molar properties. In order for us to apply the whatever we have learned in the thermodynamics for separations, reactions, mixings, everywhere the partial property of the component will come. What is the partial property? You know, in thermodynamics we have to deal with the solutions. That is mixture of different components in a solution, whether that is for the reaction purpose or the separation purpose. Whichever may be the thing, we have to deal with the solutions or mixtures. The property of the solution, let us say volume of the solutions or Gibbs energy of the solution, enthalpy of the solutions or entropy of the solutions, the solution the formed by components. Example, if a solution is formed by A plus B, then what is the volume of the solution? It is the volume of A plus volume of B. This volume of A plus volume of B has become partial property of the total volume of the solution. Like that, in a solution, because of this components, the total Gibbs energy of the solution is a Gibbs energy of A plus partial Gibbs energy of the B. What is the total entropy of the solution? It's a partial entropy of A plus partial entropy of B, like that. Partial properties of components play important role in solution thermodynamics because our ultimate agenda is to separation, purification, reaction. So partial properties are important. Example, let us come to the session. So you know the total Gibbs energy of the solution is a function of pressure dP, function of temperature dt, plus sigma mu I dni. This mu I is nothing but chemical potential of the solution. Because reaction, separation, mixing, everything is happening because of the single potential which is called chemical potential. The potential, the energy that contained within the molecule is responsible for separation, purification, mixing, reaction, anything that happens in the world of chemistry or anything. So that is why this mu I is nothing but chemical potential of I in the solution, which is nothing but partial molar Gibbs energy. The partial molar, that means this mu I, the another name, the chemical potential, the another name for it is nothing but G bar I. That is partial Gibbs energy in the solution of I is nothing but the chemical potential, which is generally represented by dou G by dou Ni. Any Gibbs energy with respect to its moles is called chemical potential of I. If it is A, example, in a binary mixture A plus B is there. What is the chemical potential of A? It is nothing but total Gibbs energy with respect to the moles of A is called partial Gibbs energy of A. If it is B, total Gibbs energy with respect to the moles of B is nothing but partial Gibbs energy of B, which is nothing but chemical potential of B. That is why mu I is a chemical potential, which is nothing but Z bar I, partial molar Gibbs energy of I with respect to the moles of I. And similarly, as I talked about, the partial properties make the total property. So there existing a property like partial, you are going to see, if you refer to any books, you are going to observe partial enthalpy of I, partial entropy of I, partial energy of I, partial volume of I, everything you are going to see. So for you to understand, to get a grasp of partial molar properties, you need to fix to these notations. Because if you to refer to the very good books like Smith and Van Ness, Chemical Engineering Thermodynamics by Smith and Van Ness, and they have used the notations, because we have to deal with the solutions containing different molecules. That total solution property is represented by capital M. M can be enthalpy, M can be entropy, M can be internal energy, M can be Gibbs energy, anything is there. M representing total property of a solution. M bar I, that means M bar I is representing, just like the Z bar I is nothing but partial molar Gibbs energy, M bar I is nothing but partial molar property. M could be H, N could be G, M could be S bar. S bar is representing in a solution what is the contribution of A. In the solution, what is the contribution of B? That is nothing but M bar I. And the third is Mi. Mi is nothing but pure property. If only A is there in the container, the property of that particular A is represented by Mi, Ma, Mb. So M total property, M bar I partial property, Mi is the pure property. That what has been represented here. M can be anything. So let us, okay, what is the importance of partial property? Imagine a container or a containing molecules of A, the another container containing the molecules of B. The property of this, because it's a pure A, the property of A is Ma. It could be Gibbs, it could be enthalpy, it could be internal energy, anything is. This property of pure B is Mb. Okay, imagine 1 mole of A is nothing but 6 moles, because just for calculation purposes, and 6 molecules of A is 1 mole of A, 6 molecules of B is 1 mole of B, 6 molecules of A plus B is the 1 mole of A plus B. Okay, let us mix these two solutions in a container. Here again 6 molecules of A is there, 6 molecules of B is there. The property of A is Ma. Okay, the pure property of A is Ma. The same property will change once it comes in the solution and become N bar A. Why? The property of A will be affected by B, the property of B will be affected by A. So the pure property will not remain the same. Okay, if it is in pure state, it is Ma. In a mixed state, it is M bar A. Here in pure state, it is Mb. In a mixed state, it is M bar B. Ma is not equal to M bar A. Okay, why this happens? Because any property will change when one component is mixed with another. Okay, if B is present along with A, there might be some interactions between A and B which will cause the property to change. In a pure state, it is having one property. In a mixed state, it is having the another property. So that is why partial molar properties are important, because the property changes happens inside the solutions or inside the mixtures. For example, okay, from this partial molar property, you get the summability relationship. What is the summability relationship? What is the ultimate agenda? To find the mixture property, because chemical engineer has to deal with the mixtures. So if I am mixing A and B, what is the total property, okay, of this container? One example, if a container consisting of molecules A, another container consisting of molecules B, if I mix these two in certain fractions, example 50% of A, 50% of B, I have mixed in another container, then what will be the property of this container, which is represented by M? Then how I can calculate the property of M? M in ideal case, sigma xi mi. That means xi is nothing but fraction of A that is mixed. Xb is nothing but fraction of B is mixed. What it is mixed? The property is mixed. Ma, it could be Gibbs energy, it could be enthalpy, entropy, anything. Okay. Then total property of the mixture is Ma Xa plus Mb Xb. That becomes the total property of this mixture. What happens in the non-ideal case? The non-ideal case, sigma xi m bar I, instead of mi, it becomes m bar I. If I expand, because there are only two components here, xa m bar A plus xb m bar B. Why? Because Ma is not equal to m bar A. Why? Ma, once the pure A is in the mixed form, the property of A will change. The changed property of A is nothing but m bar A. In ideal cases, Ma equal to m bar A. But everything is realistic, is non-ideal case. Therefore, m bar A is not equal to Ma. If m bar A is not equal to Ma, that means partial property is not equal to the pure property. Then inside this summability relationship, the total property of the mixture is a combination of partial property. XA m bar A plus XB m bar B. So in non-ideal case, MA is not equal to m bar. MB is not equal to m bar B. So let us see one example. In the example, we are calculating the volume, molar volume of the mixture if I mix certain amount of A, if I mix certain amount of B. What in ideal case, what is the molar volume of the mixture? In non-ideal case, what is the molar volume of the mixture? That is what we are going to see in the example. So you can able to get the concept of partial molar property within one lecture itself. Okay, let us see. Hi students, let us continue the class. On one side of the board, I have found the solution molar volume when we use the pure molar volumes of A and B. One is for the ideal case, one is for the non-ideal case. In this example, we are going to measure what is the molar volume of the mixture if I mix pure A and pure B for the ideal case. And given the molar volume of A is 1 centimeter cube per mole, molar volume of B is 2 centimeter cube per mole. And imagine 50% of A and 50% of B I have mixed in this in a container. Now I have to measure what is the molar volume of the mixture. Let us use the summability formula for the ideal case. The total volume of the mixture is combination of Xi and Vi. Because I am doing it for the binary case, if I expand this sigma, then it will become XA VA plus XB VB. VA and VB are the pure molar volumes of A and B respectively. Now if I apply this in this formula, and you can see my molar volume of the mixture, if I mix 50% of A and 50% of B, I get 1.5 centimeter cube per mole. And in a nutshell, if I take a mole of A, its molar volume is 1 centimeter cube per mole. If I take a mole of B, then it becomes it is a 2 centimeter cube per mole. When I mix these two, then the resultant molar volume of the mixture is 1.5 centimeter cube per mole, which is in between A and B. Obviously, because I have used 50% A and 50% B, the total molar volume of the mixture lies in between A and B. Let us take for the non-ideal case. Same, everything remains the same. Pure A and pure B and mixture, which I am mixing 50% of A and 50% of B in this mixture. Then for the non-ideal case, then the total volume of this mixture is summation of Xi and V bar I. The V bar I is nothing but partial property. It's not the pure property. Because in presence of B, the nature of A will change. In presence of A, the nature of B will change. If in the solution, if they are losing their nature, then you cannot take VA and VB, because VA and VB are representing pure A and pure B. So now what is the partial molar volume of A? Example 0.4 centimeter cube per mole. The partial molar volume of the B is 1.5 centimeter cube per mole. Then you can apply the case of non-ideal. Then sigma Xi V bar A is nothing but XA V bar A plus XB V bar B. If I put the numbers, then the resultant volume is 0.9 centimeter cube per mole. That means if I take a molar volume of A, then it is 1 centimeter cube per mole. If I take a pure molar volume of a B, it is 2 centimeter cube per mole. But if I mix 50% of A and 50% of B, the resultant molar volume of the mixture or solution is 0.95 centimeter cube per mole, which is not in between 1 and 2. Here for the ideal case, the mixture property lies between the two pure properties. Here the mixture property will not lie between the two pure properties, because the nature of A is changed, because earlier it is 1. Once it comes to the mixture, it became 0.4. The B is 2. Once it comes to the mixture, it became 1.5. So this is how the molar volume of A and B is going to affect. Okay, let us come back with a new lecture. Thank you very much.